Chapter 2, The Electric Field. This chapter is quite challenging for many students. This is probably your first course where you'll be asked to do a mathematical integration and then uses a Taylor series expansion. As you will quickly find out, these courses, the mathematics courses, are set up to do everything for you. That is, they either give you an integral and say compute this, or they give you some type of expansion, series expansion, and says, does it converge or not? And even though I assume that you are a so-called expert in these mathematical operations, there's one thing for certain. In this course, you're going to be put into a position where now that's not the case. Therefore, here lies the problem. Effectively, you're going to have to be able to read a problem, set up an integral, then you got to solve the integral, and now you got to check the solution to see if it makes physical sense. And typically, that implies that you have to do some type of Taylor expansion. That's why this chapter is hard. Not because it's above you, it's just that you're being put into a situation that you've never been exposed to. So here we go. The first thing that we need to do here is that we want to start to conceptualize the electric field. I could say electric force field, but it's more common to just say electric field. And many times we don't even call it the electric field. It's more common to just say E field. Now, if two charges interact, they do this with no contact. Gravity is the same way. It's a non-contact force. The question of how they interacted took many years to figure it out, but it was first realized by Michael Faraday. And it's called a field. A field is a physical entity. In other words, it can be measured. That permeates all of space. Since Coulomb's law shows that electric interactions only cease to exist at r equal to infinity. That's why sometimes this is called the long-range force. Now, this is an abstract, discussion that we're going to have here. And one of the things that I want to say here is that there is a deep connection between charges and fields. And the word charges is a strange one, because in the language of field theory, a charge is the cause of the interaction. For example, mass would be called a charge, just like electric charge would be called a charge, but it's a generic term. In our case, charge and the electric field, as well as magnetic, are inextricably connected. One cannot really understand one without understanding the other. You can't understand a field if you don't know what a charge is. You can't understand a charge if you don't know its field. In essence, they're so similar that some people will say that they're the same thing. They're not. So, what do we know about this? Electric charge is a property of objects that connects them to their electric fields. But the field thing is about space. And I should be careful. No, I'm going to say space right now, but it's an abstract space. Charge tells us how much a charged object affects the field. In other words, charge is coupled to the electric field slash space. There's a coupling effect that occurs between these two. In other words, charges can't be stripped away of their electric charge, just as charges cannot be separated from their electric fields. You can't separate them. So in essence, I'm not sure what I said here, but it says charges cannot be stripped away of their charge. You can't discharge an electron. You can't discharge a proton. Just as charge cannot be separated from their electric fields. It's a really handy idea, right? Because you have to think about both of them all the time. These are abstract words. So now what I'm going to do here is, and I'm going to try to attempt to picture this with sketches. Okay. So here's what I'm going to try to do. I'm going to try to attempt to get you to visualize this. So one can visualize what a field does using the following process. It turns out that the process, we have to talk about one, interacting fields. Once I have interacting fields, there's an exchange of information. And once that information has been exchanged, there's now an interaction. So the information says that the interaction is either going to be repulsive or attractive. So what I'm showing you here is that this is the quantum field theory of fields. So here we go. Suppose we have charge. Therefore, surrounding the charge is its electric field. So picture-wise, I imagine that I have a positive charge. So if I'm thinking about a positive charge, and if it's a single one, then I'm really talking about a proton charge. And what you're finding here is that something surrounds it. And what you'll see here is that there's this intense red around, and then it starts to lighten up as you go away from the center here. And so what you're finding here is that where it's dark red here, that is the strongest field. And the strongest field means that we have a darker color. Right here, where it's lighter, that's a weaker field. And that here is a lighter color. So we would say that this is the E field of a proton. Again, I can't separate the charge from the field. Now, I could say the exact same thing about an electron because we have two types of charges. There are two types of fields. And in this case, we have a different field. And here I'm talking about just changing the color. But we have all of this field that spreads out, it permeates all of space and only goes to zero at infinity. So here we go. So right here is the weaker field because it's lighter in color. Right here is the stronger field, and this is the E field of an electron. Now we have interacting charges. So if there are interacting charges, the two electric fields inter intertangle with each other. So in other words, if I can just copy and paste, it might be just easier to redraw it again. So you could imagine that if I have a positive field right here, and I have an electron field right here, a negative field, what we're seeing here is that we have interacting fields. So when I look at the positive field, this thing extends to all of space. It's infinite. The same thing happens with the electron field. It also extends. And what you're seeing here is that now I really have interacting fields. So if I have interacting fields, maybe I should do this just to follow what I just said earlier. I have interacting fields. When they interact, there's an exchange of information. So if you follow, the language of quantum field theory, there's an exchange. So we have information, an exchange of information, and the way it does it for the electric field by force particles called photons. And now that we've had the exchange of information, there is now an interaction occurs. And in this case, it tells the charges that they are attractive towards each other here. So the key thing that I'm trying to say here is that all of this is communicated through the field. When Newton started talking about his law, universal law of gravitation, he didn't know how gravity affected another object. That was a mystery. And it wasn't until Michael Faraday came along that said, hey, it's this field that's doing the interaction. So, as another example, is gravitational fields. And as we've already said here, gravity is caused. But in the language of field theory, it's called the charge by mass, which is a property of objects that are connected to the gravitational field, little g. But as we said before, this is a space thing. So if one drops a ball at the surface of the Earth, we have two interacting fields. So as an example here, you could imagine that you drop a ball at the surface of the Earth. So when I look at this, I imagine that I have the Earth. So I have the Earth right here, the pale blue dot, and we know this is the Earth. And so what surrounds the Earth is what? It's a gravitational field. So now if I take a ball at the surface of the Earth, it turns out that that ball also has its own gravitational field. So in this case, this is the ball's G field. And this guy right here, this is the Earth's G field. And these guys interact. In other words, there is an attractive force here. So we're saying here that there's an attractive force. As you've studied this so much in mechanics, but the process is exactly the same. What do we have? We have interacting fields. Interacting fields tells us that there's an exchange of information. And as a consequence, there's now an interaction. And in this case, the interaction is attractive. Now, we can take this a step further. So, taking this one step further, here's what we find. We know that the mass of the Earth, of course, is much, much larger than the mass of the ball. Therefore, Newton's universal law of gravity, more appropriate to say gravitation, reads that this gravitational force is equal to its constant times the two masses, Earth times the mass of the ball, times the radius of the Earth squared. And of course, it has some direction, which looks very similar to Coulomb's ball. Well, if we're really close to the surface, it turns out that we can redefine this whole thing as the mass of the ball times g here. And that's going to be the gravitational acceleration field. Now, here's the important thing. Right here is this contains all the information of Earth's G field. So, in other words, I can isolate the G field. In other words, if I rewrite this thing, I could then say that G is then going to be the force of gravity divided by the mass of the ball. So what we've done here is that we have what? We have isolated Earth's G field. And we've seen pictures of this a lot of times. As you already know from your classes here, that this acceleration field, G, always does what? It always points to the center of the Earth. That is a vector field right there. So now, conceptually, that's what we're talking about it. And all this is saying here is that I can isolate the field part of Earth by thinking about it this way. But so Earth by itself has a gravitational field, right? This is the G field, which we just isolated. We want to do the same thing to the electric field. But now we have to take a different approach. We want to talk about the mathematical concept of the field. So when I think about a field, what do we mean by a field? And I don't want to write as much anymore because I don't want to make this lecture too long here, but I got to write a couple of things here. So a field in this course is either a a scalar meaning that it's a single value, or a vector. And when I mean a vector here, it's a set of values. Assigned to every point in space. So this is where you're seeing me say that if I say the word field, it also means space, but it's not just regular space. It's an abstract space. So, examples of a scalar field would be like temperature or atmospheric pressure. They have a single value at every point in space. Vector fields like wind velocity or gravitational are also assigned a vector at each point. We need both of them. So now what I want to do here is that I want to give you a more precise definition of a field here. So to give a precise definition of a field, we need a point assigned everywhere. So in this case, let's talk about gravity. I think gravity is the easiest one because most of you are going to visualize this. So I'm going to say it's easiest to start with the G field. Now, if I have empty space, that implies that there's no mass. And if there's no mass, there's no gravitational field. But there is a field. It just turns out that the field is zero everywhere. However, there is a zero field everywhere. So now here's the painful part of this lecture. I need to start drawing dots. So I imagine that I have a dot here. Let's start off small. Then I'm going to try to get bigger here in a moment. So you could imagine that each of these guys here is a field point. And there's nothing assigned to this field point because I have empty space. As soon as mass is placed here, we could then say the Earth, each field point has a value according to G proportional to 1 over R squared. So what I want to do is that I want to take my field here. So let's say that this is my field here. And I don't want to make this too big, but let's say that this is my field right here. I would like to add more points. Maybe I will just a tiny bit because it's useful to really see the whole picture here. So I'm going to copy this because this will be useful later. So now what I'm going to do is that I'm going to put Earth in this picture. So you could imagine that I have now placed Earth in this picture. So what happens here? If I'm close, then I have the strongest G values really close. But if I start to move out, the fields are getting smaller. And if I'm really far away, the field is really tiny. So I give it a smaller vector here. Now note that, of course, these are not to scale. It's just to give you a sense of what it's doing. So here you could see that this is a weaker field since G is small because I'm farther away. And when I go to look at these lengths, I have a stronger field here because I'm closer to the source. Now, here's where stuff starts to get really interesting. So I'm just going to repeat what I said before, but now I'm going to be a little bit more careful. The mass property has a lot of control over these little vectors. So if the mass values either increase slash decrease, then the G field vector, the G field vectors also increase slash decrease. And as I said before, there is a deep and inseparable connection between mass, the property of objects, and the G field. But that G field is some abstract space. So I'm just going to say this and not try to write it down because this is pretty abstract, but I think it's absolutely beautiful. Mass tells us how much of massive object will affect the gravitational field. But the field is about an abstract space that we cannot see with our human eyes. There is a gravitational space slash field where the interaction occurs. Why should we care about this abstract space? Well, it helps us to measure and help explain the physical happenings when we're dealing with gravity. So if I measure the strength of the gravitational field, it tells us about the mass of the object. In astronomy, when they go to look for some of these exoplanets, do they actually see the object? No. They measure the field, and from the field, they tell you that there's a massive planet there. So, in other words, what I'm saying here is that mass of an object is coupled to the gravitational field, which is also some abstract space where it lives. There's this deep coupling effect between the two. Now, because gravity is so similar to gravitation, there's a coupling between electric charge and the electric field. So then we could just transfer this whole idea here. So because electricity is so similar to gravity, then we say here that charge of an object is coupled to the electric field. But when we say the electric field, we can't see the electric field. So this interaction takes place again in some abstract space. And you'll see that a lot of the times I call this the electric space where the interaction occurs. So I'm going to try. So then the whole process moves very, very quickly here. So if I look at a positive charge, I'm going to come back here and I'm going to say, I got this thing. I can redraw this thing, but I don't want to. And so what we assume here is that to visualize it, we're going to do this here. Assume that at every single field point, one places a tiny positive charge. And this tiny positive charge is typically called a test charge, which we'll just call little q. So what I'm going to see here is that I'm going to see a picture of the electric force field. So if I come in here and I place this guy, I have this. So now I need to modify this. Uh-oh. Did I not copy this right? Oh, that's the gravitational. Uh-oh. I'm going to have to change that. Damn. So let me start doing this. This is the one thing I didn't want to do. So what I'm seeing here is that I have all my field points here. And now what I'm going to place here is a positive charge. Now, a positive charge, if I have a little test particle at each of these field points, then they feel a repulsive force. And as I get farther away, these fields are now smaller. And so this is the electric force field. Now, what I want to do is that I want to copy this. So now what I do here is that we said here that the field and the charge are effectively the same thing. So I can remove the tiny charges, but the field still exists. It's a real thing. It's a measurable. So now all of a sudden, I remove this field, and this is what it looks like. Because I can't separate electric charge from the field. So they look one and the same, but there's no test charge. That's exactly the same thing that we talk about with Earth's gravitational field. We know that there's a gravitational field around the Earth. Do you have to drop a ball to tell you that it's there? No. It's a real thing and it's measurable.